Hello everyone, I am Maulana Jihan Alfana from Indonesia Raya Politeknik. Thanks for the chance that had been given to me. In this moment, I want to present about experimental quasi-static test for the energy absorber tube in high-speed train. Okay, in many different studies have been conducted on the feasibility of colliding train structures, but the main challenge is the limited dimensions of their front end, which mostly limits their energy absorption capacity. This signifies it is necessary to have several design considerations to ensure a more efficient energy absorption capacity. Another study by Hosni Tehrani studied the crashworthiness design at the end of a high-speed train and found that a longer and slimmer nose can absorb energy better. We can see at the picture the impact energy absorbing device started from the vehicle frame structure, the train body structure, and the energy absorbers tubes. The purpose of this study is to determine the effect of varying the tube length on the energy absorption capacity and the deformation pattern produced. The research method that I used this is an experimental study conducted through a direct test using a UTM or universal testing machine. The goal was to obtain the data on the first reactions and the deformation patterns. The crash box used was designed in the form of circular tube with the independent variables stated to be the length varied between 100mm and 200mm, while the dependent variables were the energy absorption and the deformation pattern. Meanwhile, the control variables include 10mm per second crash speeds, 1.5mm tube thickness, and a 50mm outer diameter. The material used to design the crash box was aluminum type 6063, and the properties are listed in the following table. Moreover, the quasi-static test was conducted using a UTM with the impactor and pedestal observed to be in the form of rigid objects and was used to press the crash box tube at the speed of 10mm per second and a gravity of 9.8mm per second. We can see the table of property of the aluminum material itself and the schematic diagram of the experimental quasi-static test. And we got the results. Several characteristics were identified in studying the application of crash box as a passive security device, and these include IPFC, MF, SEA, and EA, while the experimental quasi-static test showed the deformation patterns. This figure shows the relations between force and displacement on the crash box tested as a function of its resistance to quasi-static compressive loading. This implies the reaction force of the impactor in the shorter design was evenly distributed and more stable, while the longer size was unstable and allowed a buckling mechanism. And we can see there are 4 indicators that are formed: initial peak force, mean force, specific energy absorption, and energy absorption. From those graphics, it shows that the impact energy of the impactor when it hits the crash box tube was converted into strain energy, which subsequently caused a change in the deformation shape. The low energy absorption value in the long tube dimension is caused by an uneven or stable load distribution, which led to buckling. And the next is the deformation pattern was formed when the impactor hits the crash box. It was discovered that a 100mm crash box has an imperfect pattern compared to the 200mm dimension. We can see the figure that it shows the difference of folding mechanism from the 100mm tube and 200mm tube. And next is we can see at the figure a final deformation pattern. This figure shows that the crash box with a shorter size experienced better deformation. Hence, the load was distributed evenly and stably. When the impactor hits the tube subsequently formed a ring or concertina deformation pattern from the top end to the bottom end, and this has been proven in the previous study to have the best absorption capacity compared to other patterns. And we got the conclusion that the experimental results show that the crash box with short dimension of 100 mm has a superior value in the terms of 4 indicators started from IPFC, MF, ACA, and EA. Moreover, its deformation formed a concertina pattern, while the long dimension experienced a buckling mechanism. This implies the trainer should be designed in the longer tube as a passive safety technology due to its lower IPFC value, which indicates it is safer during the initial collision. It is, however, important to note that this choice has the potential for a buckling mechanism that can reduce its energy absorption capacity. And thank you for your attention. Sorry for making mistakes, and goodbye.